Cs50. All right, welcome back to the end of week 1. This is our last Friday lecture. Henceforth, they will be Monday and Wednesdays only. A couple of announcements. So 0 new handouts, but there is code outside if you didn't get it on Wednesday. Office hours will be held one last time this evening for those of you who want to hang out in a group and work on Scratch projects or just get help from the teaching fellows and CAs. Cabot Dining Hall and Quincy Dining Hall per this. That is entirely false. No more office hours for PSET 0. But they will be held for PSET 1 onward. I'm misremembering our own schedule. So office hours will generally be offered on Sunday, Monday, Tuesday, Wednesday, Thursday evenings. At different supplies of staff members. So do check the course's website if you would like help with PSET 1, which will be released on the course's website at 7 p.m. tonight. So this coming Monday, we won't have proper sections just yet with your own intimate classrooms with single teaching fellows, but rather we'll have a few super sections on Monday, Tuesday, and Wednesday. Check the course's website to find out the schedule. These are meant to help you not only with the first couple of weeks' material, particularly the C and Linux stuff, but also to help you with PSET 1, which will again be released this evening. But in addition to that, starting this Sunday, led by Marta, one of our teaching fellows will be, yay Marta, will be the first of several walkthroughs. So once per week, what we do is hold a course-wide session that's a code walkthrough, and it's really meant to help you get started with the standard edition of the PSET. It will answer such questions as, where do I even begin? What is this all about? What might be some strategies for tackling the problem set? Those will be Sunday nights. Check the website for the schedule. They'll also be filmed and placed online, usually by Tuesday. So if you can't make it, you'll still have that resource. And they are meant to eliminate questions of the form at office hours. Where do I begin? Finally, PSET 1. So it will, in fact, go out tonight. This will be your first PSET involving C and Linux, which may very well be new topics to some of you. You will find that the PSET walks you through a lot of the mechanical details that we looked at on Wednesday in great detail, so you should not feel yourself in over your head at all. And you'll find in the standard edition, which again is meant for 90% of the class, a few challenges. So the first one is going to introduce you to the world of ISBNs. Not a terribly sexy field, but these are the numbers that have been stamped on the back of most any book that you've ever purchased. Well, it turns out those aren't just random numbers. There's some pattern to them, and we can actually detect whether something is or is not a valid ISBN. And what you'll find, though very much a bite-sized problem, it'll nonetheless get you acclimated, I think, fairly well with some basic C syntax and with loops and with manipulating characters and or numbers. So you'll find that it's a nice introduction to that. But then you'll dive into something that's more about thought and more about design. You'll be tasked with solving the change-making problem. So you've probably never thought, and probably shouldn't have given ever much thought, to what the cashiers do at, say, CVS, which is when you're due some change, they look in their cash drawer, they've got some 20s, some 10s, some 1s, some change, and odds are that human goes from left to right or from right to left through their cash register in order to hand you some amount of change. And if they're doing this intelligently, or at least a bit methodically, they're probably going to try to minimize the number of bills or coins that they hand you, because right no one likes to get 10 singles back when you're owed $10. There are more optimal solutions to that problem. But thinking about it and actually expressing that algorithm that cashiers throughout the world have been executing for years is actually interesting in and of itself. And so we'll have you implement what's generally known as a greedy algorithm for solving that problem of making change. And then finally, will you implement a little something reminiscent of Super Mario 1, his little pyramid, which will be a quick little exercise in loops and in printing and such. And the Hacker Edition, meanwhile, for those of you who would like to elect it, presents slightly more sophisticated problems throughout. In particular, provides you with some sample credit card numbers and has you validate credit cards instead of actual ISBNs, as the algorithm's a bit more sophisticated. So with that said, that will be posted online later this evening. I thought I would address one thing. So we were quite it's interesting to note that in the surveys you guys have been submitting for problem set 0, which still isn't due for several hours, most of you have just regular mobile phones, which is great because it means we don't need to spend as much energy developing, say, sophisticated iPhone applications when only 10, 15% of you actually have them. So we've actually optimized now Shuttle Boy, not only for your voice, but also for SMS. Now this is a bit of a hype because this actually existed for several years, but I kind of let it die for a little while since I didn't actually fix it. Well, it's been fixed. So now you can text a message like, and the succinct might like, this. If you text a message to 41411, this is what's called a short messaging code. So there's people in the world that have these very short telephone numbers, and you for final projects will actually be able to make use of precisely this service. If you send a text message to that number and send it a message like sboy, doesn't matter if it's capitalized or lowercase, and then A and B, where A is your origin, B is your destination, like Memorial Hall, and followed by quad, or you know what, that's actually pretty tedious to type on a phone, so you can actually just use the first 3 letters, cryptic though this may be. Memquad will get you to the quad right after class. So if you actually send a text message there, what's actually happening is an interesting sequence of steps, which is a message gets sent to this number. This number has some fancy phone switching equipment for SMS. They route that request, whatever message you type in, back to one of our servers here on campus. Our server then says, oh, here's 2 inputs, A and B. Mem, qua, what is that? It parses those strings, analyzes them, figures out, oh, obviously this is Memorial Hall, and obviously this is quad, because there's no other stop starting with those letters. We do a lookup in our own database, much like this website here does, and then return a fairly succinct explanation that the next shuttle is in 2 minutes at such and such a time. So we're using a little bit of web programming. We happen to use PHP and some JavaScript here. Can you implement precisely this kind of service on demand? So more on that toward term's end, as some of you may dive in yourselves. But we left off here. So we introduced C. We introduced Linux. We talked about some of the syntax. But now we can start to do much more interesting things with this. So int main, right? Cryptic string at first. But for now, this is sort of a copy-paste job. Whenever you start out writing a program for, say, pset1, odds are it's going to be in a file called something.c. And then one of the first things you're going to do is write something like int main and then this expression in parentheses. You're not going to put the semicolon at the end because this program has no content. You're actually going to have a curly brace, some stuff, and then a closed curly brace, and that will constitute your program. And how do you make all this happen? Well, if you're on, for instance, a Mac, recall that we began by running a program called Terminal. Problem Set 1's PDF will walk you through the process of making that icon appear if you don't yet actually have it. If you're on a PC, what you'll do is run a program called Putty, which will give you a little window like this. And again, the problem set will point you at a handout online for just clicking the right buttons, typing in the right words, and you will then be connected to your so-called FAS account, at which point you're out the so-called blinking prompt. So we used a program on Wednesday to start writing a program. What was the recommended app that day? It's a little program. Nano. So Nano is this very simple text editor. It allowed me to do something like nano foo.c, and then I could just start typing some code. And there was some stuff at the top of most files. I had comments, thanks to the stars and the slashes. I had some preprocessor directives. That was the fancy way of saying sharp include standard IO or Cs50's library. So we'll see some of that same syntax again. But once I then had my program running, say hi1.c, I then ran gcc hi1.c, hit enter. I then saw nothing happen, but if I typed ls, I saw that, oh, a.out has just been created. And if I, in fact, run a.out, I, in fact, got the results of my program. So that's where we left off. Well, we can do more interesting things than that. So let's see what. We had this first, this ability to print. So this is a cryptic way of saying that printf takes one argument, which is generally called the format string, followed by some number of optional arguments. So a pattern like this, I actually ripped out of the manual, the man page, or this reference online. And that's just kind of a clue to me, the programmer. How do I use this function? Well, this function takes const char star. Well, const just means constant. And forget about the meaning for today's purposes. Char means character. But I want to have multiple characters. So in fact, today, for at least the next couple of weeks, whenever you see char star, this is going to be synonymous with a word, or more generally, a string. So a char is a single character. A char star is a string, so to speak. It's a sequence of characters, like a word, a sentence, a paragraph, whatever. So char star just means that I can pass in a pair of double quotes, inside of which is things like %d or %lld and some other things we'll see today. Now, as for the ... what do you put there? Well, you plug in whatever variables whose values you want to be substituted into the %d or into the %s. And then there's some escape sequences, and escaping is going to be something that will recur throughout programming in general, because you often need to treat special characters in a special way, and these were just some of the ones that we saw. So we then started with some math. And that was very uninteresting at first, because I did like 1 plus 2 equals 3, and then I did nothing with the answer. But at that point, we introduced the notion of a data type. So variables in Scratch are pretty much numbers, though you can also pass in strings. The user can type in a string, and that gets stored in that answer variable. But you don't tell Scratch that, you know what, I want to put a floating point value here. You don't tell Scratch, I want this to be a 32-bit or a 64-bit variable. It does all those details by itself. And after all, what 12-year-old cares about that level of detail? And that is, in fact, their target audience. Well, we need a bit more power, a bit more expressiveness. And you can, in C, as is the case with Java and some other languages, specify what type of data you want to store in a variable. And this is useful because sometimes the language will protect you from yourself. It won't allow you to perform, say, arithmetic on a string, because that just doesn't make sense. And other times it will allow the compiler, say GCC, to optimize where those things go in memory or how they're laid out. So C has these built-in data types: a char, which is a single character; a double, which is a 64-bit real value, something with a decimal point; a float is a 32-bit floating point value with a decimal point; and then an int is just an integer. And again, a quick sanity check from last time. How big was an int in, say, bits or bytes? 32 bits, right? So if you've ever heard this jargon in the media that this is a 64-bit architecture or this is a 32-bit computer, well, that's just a fancy way of saying how big are the integers that that computer uses. And it actually relates to the size of something called a register, which is a little piece of memory inside of the Intel CPU or whatever's inside that box. So if you've ever seen this advertised, and even Apple does this these days, 64-bit Xeon MacBook Pros and whatnot, it's just referring, frankly, to the size of an integer, which has implications for how much RAM you can have, how much disk space, and other things. But there's these other types of data that you can use in C. There are longs. Now, longs is a bit of a misnomer, at least these days, because a long is how many bits? So it's also 32. And we saw that because very quickly at the end on Wednesday, I used the size of operator and just printed out the size in bytes of an int and a long, and they were the same. So we have this stupid need to say not long if you want 64 bits, but long. And then short actually goes the other direction, 16 bits generally. Signed and unsigned are types. And it's technically signed int or unsigned int, but you can abbreviate by just saying signed or unsigned. As the word implies, means that you can have negative numbers or you cannot. So if you have a signed integer, what's the largest positive number you can represent, give or take? So 2 billion, because you need to go negative 2 billion if you want negative numbers. But an unsigned int gives you literally twice as many positive values, because you can now go from 0 to 4 billion, give or take. And that's actually important when you start to write programs that actually care about large data or big chunks of memory or things like that. So those are our data types. The format strings that pertain to these are several. So this is another sort of RTFM if you want to figure out what's the right one for what. But for the most part, you'll start using %s for strings, %c for chars, %d for ints, and for longs, just FYI, it's %LLD for long D. So the rest, though, are generally not going to be as useful. You can have like scientific notation and other things there that just aren't as often used, I would say. So C has arithmetic. We saw plus. We saw assignment, not to be confused with the equal sign, but FYI, you can do subtraction, multiplication, division, and this last one, which is actually a little interesting. So there's the arithmetic remainder operator, or there's slight distinctions, modulus. Now, this % sign means you can do x %y in a program, and that is similar to doing x divided by y. But what x %y does is it returns not the result of dividing one into the other, but rather the remainder if you do so. And as simple as this will prove an incredibly useful trick through all sorts of contexts when writing software. So this ability to get remainders, we'll see, will actually be a very neat trick. And this table is just meant as a reference. So it's not interesting at all to dwell on this. But C has a whole bunch of operators, right? There's a plus, minus, division, multiplication. We've seen the equal sign, we've seen, not semicolons. We'll see less than and greater than. So there's all these punctuation symbols that have some mathematical or some programmatic meaning. Well, the world had to decide which of those takes priority if you've got a whole bunch of them in a row. In other words, if you have in middle school arithmetic x plus y times z, right? Which of those operations are you supposed to perform first? Right, y times z, right? You can parenthesize it to be clear, but your teachers probably taught you if you have a plus and a multiplication, you do the multiplication first. So C has the same thing. Anytime you have multiple operators involved in some kind of statement, a line of code, someone's got to win if there's a debate as to who should get evaluated first. So realize, and we'll revisit this over time, there's a whole set of rules as to who gets evaluated first, and you just kind of learn as you go which one is more powerful than the other. So now let's start to do things slightly more interesting aesthetically. So width and precision. All right, this is a really uninteresting way of saying that we can do something like this. So let me go ahead and open from your printouts, which again we'll continue today, this bit of code here. This is math3.c. So I propose that this is a program that takes two numbers, 17 and 13, divides one by the other, and then prints out that answer. And I seem to have done a pretty good job here, right? I'm specifying my type as a float. I'm giving my variable a name. Here is the top. Here is the bottom. Divide is my operator. And OK, at this point in the story, I have my answer inside the variable called answer. So what do I then do? Well, this is slightly new syntax. Let's ignore the part I don't understand. It's not even there. So that's really just %f\n. So that means put floating point value here, then put a new line character. What value do you want to substitute in? Well, you substitute in the answer. Well, .2 simply allows us to control now how many decimal points do we want to show. .2 means give me two numbers after the decimal point as opposed to, say, an infinite number, which a real number fundamentally could be. But there's kind of a problem here. So let me go ahead and run gcc of math.c. But you know what? So I can tell my programs apart, I'm going to use -o math3 just to keep things straight. Enter. OK, all is good. I'm going to run math3 and then hit enter. And interesting. Let me go back in. So 1.0 is the answer. But 17 divided by 13, I'm pretty sure is not 1.00. So how did I screw up? Yeah, it seems to be evaluating them as integers, right? Or we're clearly getting the wrong number, but why, the wrong answer. But why might that be? Well, 17 divided by 13. Well, what is 17? You know, frankly, it looks like 17 is just an integer. If I ever write down on a piece of paper an integer, I write 17. I don't write 17.0. But the moment I write .0, now the compiler GCC knows, oh, you know what? Yeah, it happens to be equal to 17, but it actually should be stored as a floating point value. So we have that ability to remember that bit of data after the decimal point. And you know what? If I really want to do this right, let me change this to be .0 there. So now I'm taking a floating point divided by a floating point. And what happens now in C, as in most languages, is a float is sort of more powerful than an int. It kind of wins this battle. And so the return value of x divided by y here, if x or y or both of x and y are floating point values, is itself going to be a float. So if I now recompile this, let me go back to my prompt. I'm going to go ahead and run gcc on math3.c. I get back my blinking prompt. I run math3. And there it is, 1.31. Well, maybe I want a little bit more precision. Well, let me go and change this. So not 2, but let's say 9. I have to save. And now notice, again, a common mistake early on might be math3. Doesn't seem to have changed. So again, you need to recompile at this point. So I rerun gcc. And now I run my program. OK, so now I've got 9 decimal points of precision. Well, let me get a little greedy and say something like 99. I really need this to be a very precise answer. Maybe it's pi or something like that that should allow for that amount of precision. So let me recompile this. Enter. And now rerun math3. Interesting. Now, maybe that's the case, but I'm pretty sure this is a real number, which should, at least in grade school, have an infinite number of numbers after the decimal point, right? So why are we kind of bottoming out at some point and then just getting a whole lot of zeros? What limitation are we hitting? Yeah, so the size of a float in this case. So if you have a floating point value and you only have 32 bits, don't even think of bits as meaning a digit, because you need more than one bit to represent a decimal digit, 0 through 9. But that's clearly a limit. Where is the limit? You know, even I'm not quite sure. Does it say that the biggest possible float is 4 billion.0? Or does it say it's 2 billion, but you can actually have more decimals after, you can have more numbers after the decimal point? The point is that there's some finite limit limit. If you only have 32 bits, you only have so many numbers you can express. So all right, let's try to fix this. Well, if I'm running into trouble, what can I do? All right, double. But unfortunately, this doesn't really solve the problem fundamentally. Let me try recompiling this, GCC, and now run math. Whoops, run math 3. So it's better. So I've got more numbers. They're going farther to the right, but I'm still bottoming out. So the takeaway here is that floating point values in C and most any language are inherently limited. In fact, you will occasionally find that even if you're trying to represent a relatively small number, like 1, 2, 3, 4, 5, 0.67. It's not actually going to be 1, 2, 3, 4, 5, 0.67000000 ad infinitum. Underneath the hood, there might be a little bit of rounding error there. It might be 1, 2, 3, 4, 5, 0.6. 0.699999, and so with an infinite number of nines conceptually. In other words, you cannot assume that there will be precision underneath the hood, which means you should never, if you take nothing away today from about floating point values, never try to compare one floating point value against the other if you want an exact answer, because you will run into these very subtle bugs that are the result of simply computers being limited in this way. Well, let's take a look at math4.c. So this is an approach that I very simply fix the answer by making the denominator a floating point value. And that would solve this problem as well. In math 5, notice that I've done this. So this is a different syntax, but it reveals another capability that we have. So we can declare a float called answer. It's equal to 17 divided by, well, you know what? We, the programmer, know that a number like 13, though an int, could also be viewed as a floating point value. So you can force the compiler to treat what is not a float as a float if you're comfortable that that's a legitimate conversion to make. So this use of the parenthetical float right here is simply our way of saying, you know what, treat this not as an int, but as a float. And this is an instance of what's called typecasting, C-A-S-T. And this is a very simple use for it, but it will let us ultimately change characters to numbers, numbers to characters. And recall from last week when we had a bunch of volunteers up here raising their hands and not raising their hands, representing numbers. We then converted those numbers to B-O-W, bow, by way of the ASCII coding system. Well, we can do that in code. And in fact, for problem set 2 in the course, what you will do is implement a number of ciphers, so cryptographic mechanisms that convert essentially what's human readable text to something that's not human readable, but you're going to do that by way of the underlying implementation of characters as numbers. All right, well, this is kind of a basic, right? Addition, subtraction, all of this. Well, fortunately, we can use other data types too in programs, similar to what we've seen in Scratch. So C does not have a Boolean data type. So there's no notion of a variable whose value can only be true or false. We could simulate this. So if I hand you the C programming language and I tell you there's no data type whose values can only be 0 or 1, you know, how could you kind of work around that? What might your hack be, your solution? Mod2, but be more specific. What data type would I use if bool does not exist? Right, maybe just use an int and just use one of the 31 bits, right? Just impose on yourself the constraint that any time you use a variable that you want to be true or false, just make sure that you only make it 0 or you only make it 1. And yes, you're wasting some bits. OK, so let's push back. I don't need to waste 32 bits or 31. What's a smaller data type I could use? So I could use a char even. A char is 8 bits or 1 byte. And that's why we have 256 possible letters in the chart we showed last week. So 8 bits means I'm only wasting 7. That's not bad, but it's still unfortunate. But we, the course, have gone ahead and done this. So this thing called the Cs50 Library, besides giving you functions like getString and getLong and getInt, also gives you a data type called bool. And we just kind of cheat. Underneath the hood, we just implement it as an int or a char or a short and a string, where string is literally just a synonym in our code, we'll see, for char star. And you'll find that early on in the course, it's just nice to be able to assume that these things actually exist. So in fact, if I go into hi2.c, recall from Wednesday we had this example and I said, here's a string. Well, that's not technically a string because that word doesn't exist. It only exists because I'm using this library. Well, what I've really typed here, which frankly in the first or so week of the course is unnecessarily complex, is that. It's exactly the same. So this is why, at least in the first weeks, you'll occasionally see mentions of chars and char stars. But sometimes you'll see strings. But that's because very intentionally for just the first couple of weeks do we simplify some of these details. But then we quickly take the training wheels off so that you're not making assumptions after this course as to what does and does not exist. But here's what exists for the course's sake for the next several weeks. There's a function called getChar. Notice the capital G, the capital C. There's a function called getDouble, getFloat, getInt, getLong, and getString. So there's actually no getLong, as I misspoke earlier, because it's really kind of pointless, because it would essentially give you back an int. So let's go ahead and use one of these. I'm advised to try hi3.c. So we saw this, recall on Wednesday. GetString is interesting. You got to catch me when I do that. GetString is interesting because, one, it doesn't take any inputs. So printf took something we'll call arguments, something in between parentheses. GetString doesn't do that, so more on that next week, but it does return something. So again, recall that functions can take input like printf does, but they can also produce output like getString does by returning some answer that you would better keep around if you care about it, as in this case here. Well, in this case here, adder, now we've got something slightly more interesting. I hard-coded a program on Wednesday that added 1 plus 2. Big deal. Not a very useful program. But what about this one? So let me go ahead and compile before we glance at the code adder.c. OK, interesting. Problem. What was the problem here, did we say? Yeah, so because I'm using Cs50's library, it's not sufficient to just say sharp include bracket cs50.h. I need to also tell GCC that, you know what, you need to link in with -l the library called Cs50. Little bit of syntax, you get used to it. Anytime you see this undefined reference, just think, oh, I'm missing the -l flag. So now I can go ahead and run. Actually, let me add my -o flag. Let me go back to gcc-o adder. Adder.c, and then the l-cs50 needs to go at the end. All right, now I've got a program called adder. Hit enter. Give me an integer. Audience participation time. 57. 12 I heard first. The sum of 57 and 12 is 69. Either that's very clever or yeah, clever. You can do arithmetic faster than the teacher can right now. Excellent. So we've written a program that adds two random numbers together. So how did that actually work? Well, we have in this file, again, the following lines of code. So we've got one printf, which is uninteresting now because it just says give me an integer. And then I have a space, a close quote. I don't have a \n, and that's how I actually implemented all of that on one line. Well, then I have this integer called x. I assign it the return value of getInt. So that's pretty basic right now. And then I do the same thing for y. And then notice you can start embedding even arithmetic expressions inside of parentheses as arguments, so to speak, as inputs to other functions. The sum of %d, placeholder, and %d is %d exclamation point \n. And I just have a comma enumerated list of the three variables I want. All right, so what can we do with this here? So this is sort of the canonical stupid program one does in typical computer science class because it's very basic, but nonetheless allows you to get started. So here is a blank. All right, think to yourself, little at-home in-seat exercise for, say, 30 seconds and no more. What is the 1 or 2 or 3 lines of code you might need to write to implement this? In other words, fill in, if you could, on a piece of paper there, how you would implement this program, and I'll seed it by saying, you know what, go ahead and use getFloat to get the input. And for those who like to use this as an opportunity just to sit there and zone out, you will be challenged to look at the person's code next to you and point out whether or not it is right or is wrong. This always seems to help. one more loop of this. So go ahead, if you would, and raise your hand if the person next to you wrote nothing down. OK, that's all right. It's to be expected. But here's a possible approach. And let's just see. Think to yourself or pat yourself on the back if you at least have a couple of these pieces right. All right, this is your first C program, simple though it is. All of this stuff up here is pretty much cookie cutter. And the comments certainly don't fundamentally matter, but are in fact a matter of good style. So let's see what I've done first. So printf temperature in Fahrenheit colon. So I didn't specify all this kind of detail. So maybe you didn't even have this, and that's fine. But I printed out some prompts. Temperature in F colon, and then get some input. This part, hopefully, you had at least mentally going on. So float F gets get float, and that's it, semicolon. All right, well, how do you do the conversion? Well, this part's relatively easy, especially even if you didn't remember the formula. Frankly, that's the one point of this little bit there. So we just need to convert that expression from the slide into mathematics. And notice there's a couple of interesting details here. So one, notice that I intentionally used parentheses here so that just like the arithmetic expression on the board, it is in fact doing the subtraction before the multiplication. And then there's one other detail that's, sort of technically interesting. And what's that here? Yeah, so I have the 0.0. So the denominator there is not 9, 5 divided by 9, because if I had just 5 divided by 9, what would the value of C always end up being? It would in fact always be 0, right? Because if you have two integers, 5 divided by 9, so that's point something, 0.4. But then if it's an int, well, you can't fit the decimal point in an int, so you throw away the 0.4, so and then you're left with just the 0. So that means 5 divided by 9 as integers, in fact, always gives you zeros, which means multiply 0 by F minus 32, it doesn't matter. It's always, in fact, going to be 0. So we fix that by specifying that we have a decimal point here. We could fix it with casting, although that would look unnecessarily complicated. But then the final answer just involves these basic building blocks. So the 0.1, %.1f means what in layman's terms? Display one decimal point. That's it. And clearly there's a limit there somewhere, but you're usually safe with just 1 or 2 or a few points of precision. Then I say capital F just to show units equals, and then I have another %.1f, capital C for Celsius, and then I plug in the values. So simple, but again, look to this, especially as you dive into problem set 1. If you're kind of thinking, wow, it looked relatively easy and trivial in class, where do I begin? Well, the basic questions you must ask are, well, one, what framework do you need in place to write a program? And you need, we've seen stuff like this here. And even this is only necessary, the Cs50.h, if you're actually using bool or string or one of our capitalized function names. We've certainly had examples where we don't even need that yet. Then you have your main routine. Then you have some basic lines of code. So let's now introduce some tricks we already had last week, conditions. So how do you write a condition in C? You simply say if, and then in parentheses, a Boolean expression. A Boolean expression might be x less than y greater than x. Very similar in spirit to what you saw in Scratch. You usually need the curly braces, just like Scratch had sort of shapes that said inside of this construct is the following code that you need to execute. The curly braces achieve that same effect. And now I've done this a few times now. This // notation, what is that probably? So it's another type of comment. So whereas at the top of this file, and most we've seen thus far, I have /* and then whatever I want, then */. So that's a multi-line comment in C. And the world, again, has just adopted some aesthetically interesting or very anal tendencies, like creating these long lines of stars or boxes like this. It's completely meaningless to the computer. It's just really a matter of style or convention. But it does mean that that comment can go as many lines as you want. By contrast, inside of my code, it's very good practice, and in problem sets it'll be expected that you comment your code. And by this we mean every few lines of code, you should have generally a single line comment. Unless you really need to elaborate in more words than a single line allows, you would have / and then a little comment that's useful for you, the reader, so that when you go back and look at this code again, you don't have to sift through all the minutiae of C. You can just look at your own words as to what this chunk of code did. And certainly from the course's perspective, it allows the teaching fellows then to understand maybe not what your code does, but what you intended it to do. So realize there's that motivation there. But this matter of style, choosing variables that are intelligently named and describe what they do, commenting your code every several lines, or actually explaining particularly complicated blocks of code that you yourself might forget how they actually work because you were just so darn clever, is again a matter of good style. But we can stack these things. So we have if-else conditions as well. If, parenthetical, then you do some stuff inside curly braces. Else, you can then go and do something else altogether. So let's actually see this here in code. If I go ahead and open conditions1.c, we have this code here. So the top is again cookie cutter. This program does what? So let's see. This is again conditions1.c, ask user for an integer. All right, so I've got some printf there that does that. Then I'm doing some basic Cs50 library stuff, get int. Now I've got an integer. And now, OK, I'm using this condition. But I told a little bit of a lie a moment ago. What's missing from my own code here? So those curly braces. So again, silly little syntactical detail, but a tendency people have is if you only have one line of code related to a branch for the if or for the else, you actually don't need the curly braces at all. So if you have one statement that you want executed beneath the if or beneath the else, you can simply do it very correctly as I've done here, and therefore not clutter your code with what ultimately boils down to just unnecessary characters like, OK, now I can go in there. I can put this in here. I mean, this really hasn't added anything. And in fact, it's made my page wider. It's sort of not quite as fast to read. So again, that's why people just sometimes omit those things. If I had done something like this, though, I'll get into trouble. So if I did this, you picked a negative number and say something like, that was stupid, exclamation point, \n, semicolon. So you can indent all you want. The compiler's not going to realize this. So if I go ahead and run this program now, I'm going to go ahead and compile conditions1. I'm going to save it as -o conditions1. This is conditions1.c. Enter. OK, I screwed up again. -l cs50 fixes that mistake. Enter. So now I run conditions1. I'd like an integer, please. 44. Enter. Feels like a bug, right? I thought it's only supposed to do that when I pick a negative number like -1, 2, 3. But again, the reason is that it doesn't matter. If you've indented it, you need the curly brace. So I can actually fix this now. OK, a little curly brace there. Close curly brace there. Save it. Recompile. Bang. G. Again, executes the most recent command that started with G. Now I'm going to rerun my program with, say, a positive number, 1, 2, 3. Oh, that's good. About 4, 5, 6. Still good. How about -1, 2, 3? And in fact, we fixed that mistake there. So any questions thus far? Since I know this has been a lot of little things quickly. All right, so let's take it up a notch so that we can actually do more interesting things still. So if you want to stack these things together, if, else if, else if, else if, else if, else if, else. But again, just as some of you might be finding, or once we provide you with some feedback on problem set 0, we'll find that even Scratch programs that are like yay wide, if you're doing a lot of left-right scrolling or a lot of top-down scrolling, odds are you can implement it a little more cleanly. So, you know, it's no accident that I only depict an if, else here. If you've got 20 of these things, I mean, you're pushing the limits of what constitutes good design. And again, these are just rules of thumb I'm offering right now. And they're fairly vague, I realize, but we'll see by way of examples over time why, you know, code that starts to get this and this and this long can probably be done more intelligently. So in this case, here's the second version of this code. So here, I've actually fixed what was apparently a bug. You know what? Let me go back before we actually spoil that. And maybe you already realized it. 1, 2, 3 worked. -1, 2, 3 worked. But, now the anal mathematicians in the room should know that so 0 is neither positive nor negative. So I'm actually returning, silly though the bug is, a mistake. But notice it derives from the simple fact that I have, let me go back to the program, And let me roll back to the very original. I only have two cases. Either a number's positive or negative, but there's a corner case there. And so when we say you should be testing your own programs before you submit, just like your own Scratch program, should you be trying to figure out if you can actually break them by doing something the program doesn't intend, this is in fact a bug, but very easily fixed, because I can say else if n equals 0, then I can say something like printf you picked 0 exclamation point new line, else I could do this, else if n is greater than 0, or rather, whoops, if n is less than 0. So do I need to do this? It will work, but in this case, you're really just wasting characters because it's not necessary. Logically, there's only 3 possible conditions there. All right, so now let's look at what you can do inside those parens. So if condition or condition. So we have this ability not only to say is this and this true, but we can also ask is this or this true. And you can also string these things together. So this too is useful if you want to check multiple things at a time. Vertical bar is the or operator. Ampersand is the and operator. And here's one approach where we might use exactly this code. So this is called non-switch.c, to be distinguished in a moment from something called a switch. And notice what I've done here. If I actually want to have some kind of boundaries, lower bound and upper bound here, I can arbitrarily write this program. So if I type in the number 5, what does this program spit out at me? I picked a medium number, right? It's fairly straightforward to read that, OK, so if n is 5, well, that's greater than 1, yes, but it's not less than 3, which means this first block of code doesn't actually execute. So n is greater than 4 and n is less than or equal to 6. That works, which means this condition gets executed. But these branches, these ifs and else ifs, just as the English implies, are mutually exclusive. So in fact, this is only going to execute one of these lines of code. And the moment this checked off line of code executes, the compiler, or rather the computer, does not even look at those remaining 4 lines of code. All right, so turns out there's a different approach to this. And again, just as last week on Friday was about kind of seeding you with some basic building blocks with Scratch, same deal here. Before we take things up a level and try to do something more interesting, there's also this construct known as a switch in C and also in other languages, where if you find that you're kind of enumerating a lot of cases again and again, it's simply a matter of style. Or readability sometimes, to use this thing instead. So this is called a switch. You put the word switch and then in the parentheses a Boolean expression. Or rather, you put in the switch, you put, say, a variable. So whether it's X or Y or Z, you put in a placeholder there. And then what each of the cases do thereafter is they check, does that case match the expression? Does this case match the exception? And if so, do this. Otherwise, do that. Otherwise, if none of the cases match, do this other thing. So this construct here is essentially equivalent to saying if expression equals I, else if expression equals J, fill in the blank for the last, else. Right? So there is no actual check because that's what we mean by default. So if I pull up this version here, this is switch1.c, let's take a look how I can implement precisely that same idea. Now the code is longer, so arguably I've not really done anything better here. This is, dare say, not an improvement because even I had to scroll. But it's slightly more readable, right? Even you at first glance with that last program might have had to think, OK, greater than 1, less than 3, greater than 4, and all that. This is pretty darn clear as to what cases induce what behavior. So here, too, it's sort of a matter of style, a matter of judgment. Is this more readable? Frankly, I think it's probably a coin toss between the two. It's longer, it's clear, but technically you'll even see things like this. So technically those could be on one line. So if it's simply the length of the code we're not thrilled with, that's still pretty reasonable too. And I point these kinds of things out today because you'll see sort of discrepancies in the course from things I say versus things your teaching fellow says versus things CAs in the lab say as to how you should write your code. And that's because this is, again, just kind of a matter of style. How one writes English kind of varies by person to person. Same deal with code. What we'll do ultimately on the course's website is post a style guide of sorts, sort of rules of thumb or different approaches you can take to actually writing code. But for the most part, it's sort of an element of flair you yourselves will ultimately add to your code. Whoops. Third time's the charm. So what about this? There's a difference here. This program's not numeric, so it turns out you can use characters as those expressions. So this program simply says you got an excellent grade, you picked a good grade, you picked a fair grade, you picked a poor grade, and so forth. And it does that by way of enumerating these cases, and it handles the case sensitivity of the user's input by just saying, you know what, this case applies if it's capital A or lowercase a. And if you now think about how we would implement that in code using ifs and else, there would again be a lot of those Boolean operators like ampersand, ampersand, just as in the case a moment ago. All right, so now let's do things that are not just syntactically different, but at least visually more interesting. So we had loops introduced in Scratch. We had loops even demoed on Wednesday. Here is one of the most common approaches to a loop in C. You've got three things in parentheses: an initialization or initializations, a condition or conditions if you ampersand them together or them together, and then you've got updates, so to speak. So what does that mean? It means when you write a for loop, if you want to do something multiple times, you are going to initialize some value, like a variable, to 0 or 1. You're then going to check and make sure that variable is not greater than some threshold. And then on every iteration of this loop, you're going to do an incrementation or something like that. Well, let's actually try something very simple. So foo.c. And you'll find that foo, bar, baz, and stupid words like these are just placeholders that computer scientists use when you need to whip out a variable. So char star argv is the start of my program. OK. What's that? Oh, thank you. Actually, it'd be funnier if you just let me go for a while, but thank you. So include standard io.h. I'm not sure I need Cs50's library just yet, but here I have the basic setup for a program. So let me practice what I'm preaching here. So for, give me an integer I, assign it to a default value of 0. Let's do this so long as, say, 200 times. And then on each iteration, do plus plus. Well, what do I want to do? Well, why don't we just do something like printf? And I know this is kind of simple, but I'm just going to print out this. All right, so gcc of foo.c, enter. Now I'm going to run a.out. OK, that's a pretty damn fast program. Let's see if I can do something a little more interesting. Let me go back to this. More interesting than star might actually be to print out the number. So I could do this and then print out I. So let me recompile that, rerun a.out. OK, not very readable. Give me a quick fix. All right, \n. Still underwhelming, but let's do that. And then a.out. OK, interesting. But, wait, I thought I said 200. All right, so it's less than. So again, computer scientists or programmers generally count from 0. So if you're saying 0, I is 0 up to 100, up to 200, realize, yes, you're printing 200 values, but the first is 0, thus the last is 199. Well, we can make this even more interesting by screwing up. What if I do something like this? So I minus minus is the opposite of I plus plus, a.out. So what's going to happen? Will this go forever? Well, actually, it might go forever. But why? It's not going to go forever in the same direction, right? Because think about what's happening. Even though we haven't really talked in detail about how you represent negative numbers underneath the hood in this course, at some point you're going to run out of bits, right? So if we're what's going to happen if we keep flipping bits from zeros to ones, zeros to ones? What range are we going to probably end up in? It's probably just going to, at some point, become positive, which is mathematically wrong, but we're just starting to confuse then with the representation of a positive with a negative number. In fact, this will take a while, because we're only at, what, 800,000, and we've got negative 2 billion to go. So let me go back into this. How could I fix this and make it more dramatic, perhaps? Let me say, so long as it's greater than 0. And you know what? I don't have to do just plus plus. I could do I gets itself I times 2. So this little exponentiation, a.out. Whoops, what's wrong? What did I do wrong? So times 2. This part's right. I didn't hear it loudly enough. So it's initialized to 0, which means here, too, the loop, the condition, or the syntax is perfectly correct, but I is initialized to 0. Do the following while I is greater than 0. That never happens. And so this line here never gets seen. So a quick fix, and again, this is completely nonsensical at this point. We're trying to demonstrate a different point altogether. What happened here? It stopped. But what happened? So we kept increasing the value of I, so bigger and bigger and bigger and bigger and bigger. So think back to the light bulbs from last Wednesday, right? To keep incrementing numbers in binary from 1 to 2 to 3 to 4. Remember, we just kept changing zeros to ones, and then the ones kept kind of bubbling up until we had more ones than we did zeros. Well, at some point, you're going to run out of bits to flip, so to speak, and you're going to get all the way back down to 32 zeros. Right? The clock changes over again. And so, in fact, this condition eventually does stop us. Well, let's see. If we get rid of this condition altogether, can we at least see what's going on? A dot out. What's going on here? Multiplying 0 by 2, right? If eventually I becomes 0, if I keep trying to double it, I get stuck at 0. So in short, this is bad things. If your code's doing things like this, like there's a problem somewhere. And very clearly, are there many different ways you can screw up code like this. But what's interesting, hopefully, is why this is actually happening. And for today's purposes, realize we've hit a couple of thresholds. One, how large the ints are that we can represent, how large the floats are that we can represent. But these are things that become important when you try to actually now use them in context. So let's now use this, not to just print out numbers like this, but to do something that's at least more aesthetically interesting in the progress bar. So this is a file called progress1.c. You've got it in your code there. And it makes use of the same idea, but now I'm kind of trying to simulate what's a very reasonable program. It's not just printing some stupid numbers. It's actually indicating progress like most programs do. So I've got an int that initializes to 0. Do the following while I is less than or equal to 100%, and then increment. And now notice this, %d, and then what's percent mean? Print a percent, right? You run into these problems if percent has special meaning. So percent means give me a little percent. And this is a new feature. So sleep1 apparently is going to make this thing pause for some amount of time. GCC progress1, let me go ahead and run a.out enter. All right, it's probably not worth spending 100 seconds seeing if this thing is in fact correct. But it will in fact ultimately bottom out at 100%. That's not very interesting. I don't really want to see where I've been again and again. So let me go ahead and open progress2.c. So progress2.c operates as follows. Oh, so that's a little more interesting, right? It's not moving. And for those of you in the awkwardly close seats here, now you can see that. So now it's counting up. How did I do this? Yeah, so remember, this is, again, one of these sort of random things that at first glance doesn't seem all that useful. But if you don't want to advance to the next line with \n, but instead want to move the typewriter's head, so to speak, all the way back to the left, and then just reprint the line, essentially implementing the idea of animation, this is, in fact, one way we can do this. So you know what? I thought we'd do this. Let me go ahead and type endow.c. I'm going to do int main int argc char star argv. I got a little bit of that. I'm going to need my standard library. So include standard io.h. I want to have let's see, 4. Oops, careful, typo there. So 4 int endowment gets, all right, so I just so happened to bring this. So last year, our endowment was 36.9 billion. So let's initialize endowment to 36.9 billion. OK, so that's a lot of zeros. And actually, C will not like the commas. So let me remove those. And in fact, I've already made a mistake, which is what? So while endowment is greater than or equal to, well, now our endowment is 26.0 billion. So let's make that the threshold, 26.0000000. So that's billions. But let me get rid of the things there. And then you know what? Endowment minus minus. All right. And now let me go ahead and do this. So print endowment colon $. This isn't funny to someone out there, I'm sure. So endowment %d \n. Well, that's going to look a little ugly. You know what? Let me whip out that \r and just keep returning the reading head to the start of the line, %d. But there is a bug here. Endowment. Has someone caught it yet? You got to say it a little louder and clearer. So a double, or really we have long, long. So Harvard's endowment, curiously enough, is neither now nor then small enough to fit in the size of an integer. We actually have to whip out a long, long, so we get 64 bits, right? Because what? If we had an endowment of 36.9 billion, that's larger than the 4 billion max, even in an unsigned int. So let me change that to long, long, endowment, endowment minus, minus, and then I got to change this to a long LLD. And now let me go ahead and run gcc on endow.c. Oops, not print. Yep, there we go. A little typo. Let me recompile. Let me run a.out. All right, let's take a 5-minute break. All right, we are back, but we still have plenty of money. I went ahead and made the font size bigger. This is actually, those of you who have ever been to Manhattan and Union Square might know the clock that kind of ticks down perpetually. So that's essentially what we've implemented, and it really just boils down to something simple like \r. I'll admit, when I first kind of banged out this example, it's really kind of disturbing to see what it really means to lose dollar after dollar after dollar. I mean, just in the time I just spent stuttering, do you know how much stuff we could have bought? So anyhow, so we'll leave that running probably for several days before we bottom out. But let's go ahead and just wrap up this look at conditions. And let's see, once we've gotten some of these basic building blocks out of the way, what you can do with these same fundamentals. So the revelation in the progress example, the progress bar example, was quite simply this. So I'm going to go back real quick to nice.fas. I'm going to log back in as myself here and go into my Cs50 directory. And the code in question is this progress2. So the only change that I made really is this \r. But you'll notice in your printout that what I didn't do on the fly a moment ago and actually got away with it, I actually have this line of code here, fflush of standard out. So I mention this now just as one of these things to tuck in the back of your head. What computers often do in the interest of efficiency is, even though you might tell them do something like print this, they might say when I get around to it, essentially. So printf has this thing, a buffer, right? You're all familiar with buffers from the idea of like internet videos, buffering and all of this, kind of building up enough bytes before you then see the movie. Well, same deal here with printf even. So there's this thing known as standard output, which is essentially your screen. And it has a buffer of some number of bytes or kilobytes or whatever that the computer then uses to fill up, and only once it's sufficiently full does it display what's on the screen. Well, in the case of the computer I ran this on a moment ago, I changed the number and the change got written out immediately. But this fflush here essentially says flush the file, because standard out, we'll see later in the course, is essentially a file. Just means spit out what I just told you to right now, right now, right now. And then sleep, meanwhile, apparently takes a single argument, a single input, in this case a number of seconds, 1. And the reason I was able to use this thing is because I also included this header file here. So in fact, you'll get used to this over time too. There's a command in Linux called man for manual, and you can type in something like sleep, and sometimes you need to specify the chapter of the manual you want. By default in this class, you'll almost always use what's called chapter 3 or chapter 2. Let me see if I guessed right. I did, in fact. So this is the Linux Programmer's Manual. The function in question is sleep. It's in chapter 3. And this is, again, just kind of a very concise explanation of what this function does, and more importantly, with what library it's included. It tells you what header file you need. So as the course progresses and as you start getting a little more daring and finding new functions that we just haven't gotten around to mentioning in class, you'll find that just typing man and then the name of the function with sometimes a 2 or a 3 before it will tell you how to use that function. And it's very similar in spirit to the stuff you'll see on the course's website's resources page if you go to that cppreference.com. So there's one other approach, though, that we haven't yet done that's already in your printouts, and that's this. So we said there's for loops, but I also said on Wednesday there's while loops, and there's actually another thing called a do while loop. And these two are just kinds of different approaches to solving the same problem. So in the previous version of the progress bar or the endowment program, I just used a for loop. And frankly, I probably go with a for loop way more often than I do with a while loop. just because I feel more comfortable with it. But you can do things differently. So if I know in advance I need a variable, well, like we saw Wednesday, I can declare that variable and give it a value. But then I can say while that value is less than or equal to 100, do the following. So whereas the for loop has the 2 semicolons and 3 things going on, a while loop is actually much simpler. It just has a condition which says do the following while this condition is true. So the effect is ultimately the same. Print this stuff out, flush standard output, sleep for a second, but I kind of have to manually update my counter for me because the while loop just does not give you that capability. Which one is better? In this case, it feels to me, sort of being a little anal about this, that the for loop's a little nicer because everything's kind of self-contained, all in one block of code. And this is, again, the kinds of instincts you begin to acquire over time. This, to me, feels a little messy. I got this orphaned variable at the top. I'm doing this I++ arbitrarily at the bottom. It's completely correct. It's not wrong, and it's hard to fault it. But there's something about it to me that kind of rubs me the wrong way, and so I might go with the for loop approach. But again, there's different approaches to different problems. But there's also this construct, which actually has a fundamentally different meaning, and that's the do while construct. Do followed by curly braces, some stuff, and then the while loop is at the end. And that's the key difference here. So the do while construct, as it implies aesthetically, does something, the stuff between the curly braces, then it checks its condition, and if the condition is still true, it does that something again. Rechecks, does it again, rechecks. Whereas in the previous case of the typical while loop, it's while condition, which means the condition gets checked first, then some stuff maybe happens. The do while loop is fundamentally different because it definitely does what's in between the curly braces at least once. Now, why might this be useful? Well, let's put it into context. So here's an example called +1.c. So this example here does, oh, OK. So and this is actually representative of the typical use, frankly, for a do while loop. Anytime you want to prompt a user for input, but you don't really trust them, you think there's a chance they're going to mess around with you or screw up their input, you want them to do something once, and then you want to check did they do it right, because if not, you want them to do it again. So you want them to try something, then you want to check a condition, and then you want to do it again if they screwed up. And that's precisely what's going on here. What do I want to do? Well, I want to print out, I demand that you give me a positive integer. Then I get the int. But notice this order of operations here. Code is generally executed top to bottom, left to right, which means those 2 lines of code have already executed, which means now stored in n is whatever the user typed. While is now the condition. So while n is less than 1, what do I do? Well, if the user just did something, but n is less than 1, that means they did the wrong thing, which means I should go do it again. And if they still screw around and give me -3, let's do it again. -4, do it again. +6, OK, this condition is now false, and so it breaks out of this whole construct. So now, if I go ahead and compile +1.c, oh, same problem again. I need to link in CS50's library, LCS50. But again, recall the trick from Wednesday. Make +1, because of the way we've configured the system, should automate that for us, even though it's going to dump some more detail on the screen. I can now run +1, enter, -4, -3, -2. That's because of the do while loop keeping in. If I say something stupid like monkey, then it's also going to catch that. You didn't see that one coming. So it's also catching that. Well, because one of the things CS50's library does is if you call the getInt function, we were persistent. We spent a good amount of time thinking through how to implement the process of getting an int from a user. So we, in our library, are actually doing some error checking. We're not checking. The function is called getInt. We're not checking if it's positive or negative, because the function is called getInt. It's not called getPositiveInt or getNegativeInt. We're just getting an int. So you have to do some of the error checking, but we can at least detect when someone types in something random like monkey or banana or random characters at the keyboard. But then if you finally type 6, thanks for the 6. And it finally detects that it's actually a legitimate number. Well, let's take a look at this second version here. So this is different. How? Well, it doesn't do anything fundamentally different, but thus far we've had some fairly small programs. I can introduce other variables if I want. So there's this notion of a Boolean variable, which we promised existed. Its value can only be true, TRU, all lowercase, or false, FALSE. But realize that's only because of CS50's library. Now, other languages, C++, Java, have true and false built in. C is pretty old. It didn't have true or false. So we've re-implemented those. And you declare a Boolean variable with bool, the word you want, the name you want to give the thing, and then assign it a value. And now notice what I'm doing. You know, I actually don't care in this program what the user is giving me. I'm calling getInt, but I'm completely disregarding the return value except to check if it's greater than 0. I'm not storing it in any value. If it is in fact positive, I change the value of thankful to true. Notice I didn't bother with curly braces around the if because it's just one line of code. And now my Boolean expression has just changed to be this here. But a common mistake might be this. You know what? I'm very used to seeing equals, meaning if something's equal to something, I write one equal sign. Now I just changed the program as follows. I changed it to a single equal sign. Make +2. Let me go ahead and run +2. It's warning me because I'm actually being a little loose with my code as it is. Let me give it a -23. So why is this all of a sudden broken for negative values? What's going on in this line of code? So I do this, then what happens? I'm assigning the variable called thankful, no matter what, a value of false. So then think about order of operations. The parentheses are outside, just like high school math. Parentheses outside means do what's inside first. So thankful gets assigned the value of false. OK, so what's the value of that whole expression now? False. So inside parentheses now is while false. So that immediately means you don't repeat that loop because it's false. And you only repeat loops when it's true. So you immediately break and therefore say thanks for the positive integer, even though it wasn't a positive integer. So here too, another sort of common mistake. It's a little annoying that the world chose equals equals and just equals for different meanings. And in fact, it's really going to annoy you when we get to PHP. And not only is there equal and equal, there's also equal, equal, equal. But there's no equal. There's 3 of them, and they all have different subtle meanings, but a common bug there. So let's take a look at one final version of this. So +3.c is a little more elegant. So I got a little fancy or a little lazy, depending on how you look at it. What's the one key difference toward the bottom of this program? Yeah, so this bang sign. So bang has a meaning at my shell. My blinking prompt, if I do bang or exclamation point and then G, that gives me the last command that started with G. But that's at your shell, the blinking prompt. This is now C code. In the context of C, the exclamation point or bang inverts Boolean values. If it's true, it becomes false. If it's false, it becomes true. So this bang variable name is actually a very common syntactic trick just because it looks kind of nice and clean to say while something is not true, you literally say not variable name. And this inverts its value. And because, again, I've chosen my variable names cleverly, but in a straightforward way, the fact that I called it thankful means that even though I'm now writing C code and not pseudocode and not Scratch, while not thankful is in fact the translation of C into what I might say in English. So this too speaks to the niceness of choosing variables appropriately. It's a little more clear than like while not X. Like while not thankful, again, is all the more clear. So that's all kind of interesting. And you now have these building blocks. You'll need all those building blocks for the problem set. But you can do, and we will do later in the semester, even more powerful things using sort of more familiar tools and APIs. So again, this is meant as a teaser for what's ahead, because I realized that in the first week or so of the course, you just made some pretty sexy Scratch projects, loud and interactive and whatnot. And now we kind of have to take a step back and have you implement change making and these smaller little Mario puzzles. But we'll very quickly build back up to things more familiar. So this is a program. If you're looking for something to do on a Friday night or procrastinate, and you've never played with Google Earth, Google Earth, download it. It's free. And this is sort of the Earth version of Google Maps that Google acquired from a company. And frankly, you can take little virtual vacations with this thing. So if I type in 1 Oxford Street 02138, this is actually going to whisk me away, if you've never seen this before, to the Science Center's address. Notice that we're going to zoom and zoom and zoom and zoom and zoom. Gets pretty uninteresting quickly. But aha, there we go. Gets a little spooky at some point if you've not played with this stuff. You can do some of this in Google Maps, but you can do things like change the elevation you're actually looking at. This gets kind of trippy. It's even cooler when you do it, frankly, on an iPhone these days with the accelerometer. We can do things a little fancier. This is going somewhere, don't worry. So Paris, France, we can head over there. Frankly, it's just cool doing this sometimes. All right, so now I'm zoomed in on Paris, France. And just to show you what's really cool these days with, say, graphics, let me go ahead and zoom in, if I can find it, from thousands of feet above, the Eiffel Tower, which is there. I'm going to click a little radio button here. I'm going to keep zooming in. It's really rather trippy, frankly. All right. Zoom in there. Yeah, come on. My Mac does not quite keep up with the computational needs here. So it's pretty darn cool. OK, so what's the relevance to CS50? So toward the end of the semester, one of the problem sets will actually be to implement this thing generally known as a mashup, where you actually take some data set, another data set, or some kind of graphical interface and do something with them together, whether it's Google News and Google Maps or Google Earth. What's really nice is that companies like Google provide what are called, again, application program interfaces, which means they're code, they're libraries that, similar in spirit to these .h files, you can use in your own programs, whether you're writing something in C or PHP or in JavaScript. And so the demo I thought I'd show you, just to think through a problem, we still have a ways to go, amazingly. Just to show you how we might think through this, I whipped up this little demo here. So let me go ahead and go into this directory. Give me just one moment so that we end right on time. So I'm going to go ahead to CS50, going into our course's web server, which lives elsewhere. I'm going to go into our lectures directory, the source code and map, and all of this is available online. And what I did in advance of today was a couple of things. So one, even though it's not due for several hours, a bunch of folks have submitted the surveys at the end of problem set 0 and provided their hometown addresses. So all of this has been scrubbed, so we don't know who's from where. But we have in this CSV file, comma separated values file, a whole bunch of hometowns from people in this course. Yes, you might have seen yourself scroll past really fast. So a reasonable question to ask, and a question you'll be able to answer at the end of the semester, is what can I do that's interesting with this? Well, Google Maps, for instance, provides you with the ability, as you probably know, to embed a map in your own personal or corporate website. That's pretty easy. And using a language called JavaScript, can you grab data like that from this text file and actually embed it into your own map? But that begs the question, how do you go from one to the other? Well, one of the things we'll be able to do ultimately is take what's an Excel file. So a CSV file is something you would generally open in Excel. But if you've got 200 names, 300 names, and hometowns, odds are you don't want to be doing copying and paste all day long. It will certainly take forever. So there's these things called scripts. And in fact, and I'll leave this available online, I wrote this little script. It's not many lines of code. And in fact, even though it's written in PHP, notice some familiar ideas. There's a loop in PHP called for each. I'm apparently iterating over things called hometowns. And long story short, what I did with this little script was convert the Excel file, the survey.csv, into what's called XML, or really KML, which is a markup language for mapping programs. And the end result is that I'm able to do this. If I go ahead to any old browser, go to cs50.net/lectures, and pull up our source code for today, and go into the map directory therein, what we will see is this. So frankly, it took like 10 minutes of effort after downloading the CSV file from the survey program that we're using. And none of you apparently live in Cambridge and have submitted yet. But if we start zooming out, each of these little bubbles represents CS50 students. And it's really neat. Some of you are really from pretty far away. And this is only some of the students in this course. So with that said, that's where we're going. You've got piece set 1 in your hands as of tonight. We'll see you on Monday.